the second period, which have s and p orbitals, where things start to get a little messier. So again, reviewing some certain things, that the number of atomic orbitals that contribute will form the same number of molecular orbitals. Orbitals prefer to combine with similar orbitals. It's kind of like this orbital caste system. But also, the more overlap creates lower energy molecular orbitals, or I should say bonding molecular orbitals, but higher energy anti-bonding molecular orbitals. So why am I bringing up overlap? Well, if you think of our sigma and pi bonds, so remember that sigma bonds are concentrated directly between the nucleus. So any sigma bond that forms is going to have a lower energy than pi bonds. Remember, we had those p orbitals that would be like this, and so the pi bond would be up here. So notice how that one pi bond there, those electrons are a little farther away from the nucleus. So they have slightly higher potential energy. And again, Pauli exclusion principle, only 2 electrons to 1 molecular orbital. Okay, so let's start. I'm just going to do one example here because this does get very, very complicated. If we look at nitrogen, okay, so we're going to say nitrogen is homonuclear. This means that nitrogen has 2 identical nuclei in the bond. So we're going to ignore 1s and we're just going to jump right ahead to 2s. One of the things about molecular orbital theory, it's sort of saying that all the electrons are somehow interacting. So those 2 s's will form a lower energy sigma 2s and a higher energy sigma star 2s. We get into our p orbitals. Once we have p orbitals, we could have sigma bonds that overlap directly in between nuclei, and we can also have pi bonds from the p orbitals that sort of go in parallel to those sigma bonds. So the sigma bonds will make a lower energy. Notice that I'm going to say sigma, but it's going to be a 2p sigma. And then a slightly higher pi. Now I'm not doing this so well, but the pi also comes from 2p, getting quite messy, and this is also slightly lower. Now, slightly higher than these p orbitals in energy is our pi antibonding, and higher than that is our sigma antibonding. Okay, so it's going to be favorable when electrons go into these bonding orbitals, but it's going to be, oh, and I should say that there are two of these pi bonds. Sorry, because we have 3 p orbitals. 1 p is a sigma, 2 of these p's are pi's. So again, it's favorable for them to go into bonding, not so great when they start to go into antibonding. So we know that nitrogen is 1s2, 2s2, 2p3. So, and 1, 2, 3, 1, 2, 3. So let's start putting things together. So 1 electron from here and 1 from here go into that sigma. 1 electron, 1 electron. Oh dear, we've gone to higher energy. Not so great, but let's keep going. So we get 1 electron from here and 1 electron from here. They go and they fill up this energy level. Now remember from Hund's rule that electrons don't like to share orbitals first. So say this electron might go here and that electron might go there, and then we have this electron going here and then that electron going there and filling up the whole thing. And now we've actually used up all of our electrons. So notice here, hey, no electrons in our antibonding molecular orbitals. This is a good thing. Now, I'm not going to talk about these 2 orbitals below because they will, when we think about bond order, if we think of bonding minus antibonding, those are going to cancel out. So how many bonding electrons do we see here? 1, 2, 3, 4, 5, 6. 6 bonding. And then we think of how many anti-bonding? Well, minus 0 times a half. Notice the bond order is 3, very much like there are 3 triple bonds. This theory is kind of interesting in that it also helps explain certain properties that would be hard to explain if we just did plain old Lewis structures. For instance, a property called, paramagnetism and diamagnetism. So if we were to look at paramagnetism, this is when molecules with unpaired electrons are attracted to a magnetic field. The opposite would be diamagnetism. Molecules that have completely paired electrons are slightly repelled. Now, if we were to go back, and I erased it, I hope you remember that when we looked at nitrogen, which had that triple bond, that those bonding orbitals, notice how they were completely filled, and nitrogen was completely paired up. So nitrogen, N2, is diamagnetic. However, if we look at oxygen, so oxygen, we will just go directly to our 2p's. So oxygen ends with the configuration 2p4. So 1, 2, 3, 4. 1, 2, 3, 4. Now, 3 orbitals can make, 6 orbitals, 3 from each atom, can make 6 bonding and anti-bonding molecular orbitals. So remember, we have that sigma that comes from 2p. We have 2 more p's to deal with, so we have pi 2p. We look at, and then the opposite of the pi 2p, the anti-bonding one, and the sigma 2p. So let's start placing electrons. 1 electron from each, paired up. So this is filled, so we have to move on. 1 electron, there's 2. How about I start canceling them out after I've used them. Another electron here. And another electron here. This is filled. If I now follow Hund's rule the same way I would with atomic orbitals, this electron is going to be alone, and this electron is going to be alone. So, notice, according to molecular orbital theory, these 2 electrons being unpaired makes oxygen paramagnetic when we see this in the lab. And it agrees with that when we see it in a lab. If we were to do our good old Lewis structure, right, oxygen looks like this. Do we see any unpaired electrons when we look at a Lewis structure? No. So if we were to look at this sort of definition of paramagnetism and diamagnetism, we would expect to see that in lab, but that's not what happens.